Hello, welcome to Forest Learn. In this video, you can try a 1-mark question on wave-particle duality, which is similar to the kind of question you might face in the multiple choice section of an exam. Let's take a look at it. An electron accelerated from rest across a potential difference v has a de Broglie wavelength of lambda. Had the potential difference been twice as big, what would the de Broglie wavelength of the electron have been, in terms of lambda? Please pause the video and have a go at this yourself. And when you're done, unpause it and we'll discuss the solution. Okay, welcome back. It's a good idea to draw a little sketch to help you visualize the problem and get a sense of what's going on. So what we have here is we have an electron, which I've denoted by this solid circle here, which is being accelerated across this potential difference v, which exists across these two charged plates. So you see here we've got a negatively charged plate, metal plate, and over on the right here we've got a positively charged metal plate. So basically what's happening is that the electron is being repelled by the negatively charged plate, right? Because the electron itself is negatively charged, and like charges repel one another. And at the same time, the electron is being attracted towards the positively charged plate on the right. Remember, unlike charges attract. Now the question tells us that the electron starts from rest. So let's add this in to our diagram here. And let's also add in a final speed of v when the electron makes it over to the right hand side. So even though the question hasn't told us anything about a final speed, there's nothing stopping us from drawing it in. Also note that this final speed here is a little v in comparison to the voltage or the PD, which is a big V. So hopefully you won't be confused by these two v's in this video. I'll try to make sure that they're sufficiently different in size. Hopefully it should be clear which v I'm talking about. Before we go on, why should we even worry about the final speed? Recall that the de Broglie wavelength, lambda, is given by Planck's constant, h, divided by the momentum of the particle p. And recall that momentum for a matter particle is given by m, the mass, times velocity. In the de Broglie relation, p here is really just the magnitude of the momentum. So we can safely talk about the speed, the final speed of the particle, rather than its velocity. So the de Broglie wavelength depends on the final speed. And if the accelerating voltage or potential difference big V changes, that's going to impact the final speed. And therefore that will determine how the wavelength changes. So figuring out how the final speed changes is the key here. Now, as the electron accelerates to the right, its kinetic energy increases. But remember, the law of conservation of energy tells us that energy can't be created or destroyed, only transferred from one store of energy to another. So as the electron gains kinetic energy, it must lose an equal amount of electrical potential energy, similar to what happens when we drop a ball in a vacuum. It gains kinetic energy and loses an equal amount of gravitational potential energy. So the energy transferred, or the work done when a charge Q moves across a voltage big V, is given by W, the work done, is equal to Q, the charge, times the voltage, V. And the charge here, Q, is simply the electron charge. We can just work with the magnitude of the electron charge, so just E times big V. Now, we can set this equal to the final kinetic energy of the electron. So the kinetic energy it has just as it reaches the right plate over here. Because that's precisely the amount of energy that's been transferred once the electron makes it all the way over to the right. So we can say that this is equal to, the work done is equal to half m, the mass of the electron, times the final speed of the electron, v squared. Now if we rearrange for v here, the final speed that is, That's simply equal to 2 times E times the voltage V over M, all square rooted. Now from this, we can work out the effect on the final speed if the potential difference, big V, doubles. Let's call the new speed, the new final speed, V prime or V dash. And this is equal to 2E times the new potential difference, which is twice the old potential difference. So we can write here 2 times big V divided by the mass of the electron, and all of this is square rooted. Now if we take out a factor of root 2 here, we find that this is equal to square root of 2 times square root of 2E big V, the original potential difference, divided by the mass. And if you look over here, what we've got here is just the old final speed of the electron when the potential difference was just big V. So what we've ended up with here, in other words, is that the new final speed, V prime or V dash, is equal to square root of 2 times the old final speed, which we just called little v. We can now use this to figure out what the de Broglie wavelength would have been had the potential difference been twice as big as the original. Let's call the new de Broglie wavelength, again lambda prime or dash, and that's going to equal h, Planck's constant, divided by the mass of the electron, multiplied by the new final speed, v prime. And we worked out that v prime is just equal to square root of 2 times the old final speed. So let's just make that replacement. M times root 2 times little v. And if I take out a factor of root 2 or 1 over root 2, like so, we find that we end up with this. And notice that what we've got here, h over m small v, that's just lambda, right? That's the original value of the de Broglie wavelength. So we're done. The new value of the de Broglie wavelength is simply equal to the old value divided by square root of 2. I would say this is a relatively tricky 1-mark question because we're having to deal with not only concepts of wave-particle duality, such as de Broglie's relationship, but also concepts such as voltage and work done, and therefore energy transfer. So this question is really touching on a number of different areas of physics or the syllabus, along with testing your mathematical ability to deal or manipulate algebra fluently. And if you found this question hard, I would say you should try it again in the future and see if you can do it by yourself. Just by watching this video and following along with the solution, you shouldn't be satisfied that you really understand what's going on until you can do it for yourself. Alright, so doing physics, learning physics is an active process, not a passive one. If you found this video useful, please like it, share it, subscribe to the Forest Learn channel if you haven't already, and leave a comment if you have any questions or suggestions. So thank you for listening, and I hope to see you next time.